Hey guys, welcome back to Introduction to Computer Networks at NTU. This is once again Polly. And hey, as I continue to say good morning to all of you, let's check out the what's in the announcements. How about that? Yeah, so you see Polly also again posted the link of the lecture. And the Google Meet session is now described a little bit better. Yeah, so this is for the office hour, particularly the default office hour. And for the exam sessions, when we are taking exams, you guys will need to join the Google Meet session throughout the time, okay? And for certain quizzes. And that's, again, scroll up and see what other announcements are posted before last time we checked the announcement channel. So this post was done last night. Polly was not sure how much time it takes to generate the ad codes and matching you guys. So she felt that it's better that I did that when I am free last night. So guys, the ad codes are ready. So if you've been waiting patiently and participate actively, you are on the list for the ad code. So take the ad code and go on and register. And definitely, guys, it's time to try to team up. Okay. I don't know about you guys. Of course, if you are, the ultimate introvert, of course, feel free to be your own team. But you see that it's very interesting also that working in a team. And I guess even that you're a lone wolf, eventually you need to work with people, every now and then. So I guess the college time is also a good time that you try to exercise your people skill and somehow learn from the experience and enrich your people skill. Okay. So try to team up, guys. And so as you team up, what you want to do is if you are teaming up with someone who has a smaller team number or higher team number, you'll be joining that other team. Okay. Good. So guys, try to spend some time and team up among yourselves. And as you have observed, right, having quiz 1, 2, 3, and yesterday 4, and today 5, and potentially 6, there are probably some people you will find interesting teaming up with. All right, so approach them. Don't be shy. And hey, it's all online, right? And as long as you don't see each other personally, it might be easier to talk. And that's how I see from many of you. And also definitely don't be shy talking to the TA as well as Polly. Polly might be a little bit occupied these few days. Long story short, I'm organizing a conference that would take place in Abu Dhabi next month. And since the event of the past couple days between Israel, US, and Iran, things get really, really complicated. So I'll be meeting with some of my friends organizing the conference later tonight. That's also part of the reason that I feel that when I have a free time, now I should probably do things that's the next on my to-do list to avoid me being squeezed, okay, in terms of time. So sorry that if I'm slow responding, slow grading the quizzes, it's simply because I'm a little bit more occupied with something else. And that's a huge amount of uncertainty, unfortunately. Now, one more thing that we did not went through yesterday in the announcement is this. There's a Google spreadsheet recording you guys' progress of the semester. That's ready for your reference. Okay, and we beg you to allow us time to grade and record the progress. But if you see any error, definitely let us know. If you click into link, that will take you to this page. Okay, so let me... So I think I did this, but I intended to do this, but I probably go really, really fast yesterday. So first, you will see that in this Google spreadsheet, there are 4 worksheets: PA, quiz. So look to the right of where Polly is, okay, and participation, and semester. So these are the 4 sheets there will be. So your PA grades, your programming assignment grades would appear here in the PA worksheet. And how you read the table is this. If you are Team 1, your PA1 grade would appear here in this box. So similarly, Team 2, your PA1 grade would appear here. Now, in case you find that you are deducted certain portion of the grades, or you do not receive grades, then look right. So there's this column L, that is the comments for PA1. So that will be for Polly or Henderson communicating with you how come you are deducted a certain portion of the grades, and how come the grades are not there. So sometimes we find that you guys just misplaced the file, and we couldn't find the file where you're supposed to place them. So we might communicate things about these, and to make sure that it's just a minor jitter. Okay, and if you promise that the same error doesn't appear again, we'll let you go. But essentially, this is how you read this worksheet. And this Saturday, you would complete PA1, and some of you might have completed PA1. And those who have completed PA1, feel free to go on and work on PA2. All right? PA3, I think you can also work on that as well. But for Team 26 to 28, the poor assignment is not yet in place. Okay, let me take a note there. The poor assignment. I think for PA3, you guys can work on it. For PA4, however, you would need to wait for the port assignment for Team 26 to 28 in particular. And then quiz. The quiz worksheet is where you see whether you have completed the quizzes. So far, because the teams are not finalized, and so I'm not quite sure whether a particular team will earn extra credit for a particular quiz solution. So once it's finalized, those who will take the best answer from the members, okay, and then make sure we add the marks for the extra credits. And so these are the extra credit for the quizzes. So those are the bonus part here. So if you answer the quizzes and you complete all the quizzes, you get 25% of the semester grade. And those who do exceptionally well, those teams who do exceptionally well, you will get some bonus. And those bonus add up will be 5% of the semester grades. Okay, so yeah, being thoughtful and being unique. I don't know if you like that. I think you will learn to like that eventually, because we all have our different perspectives, and it's always interesting to see each other's perspectives, and that's how you communicate as well more effectively. not just selecting the electronics more effectively, but also communicate. And you see, we are a social animal. Whether you like it or not, we are a social animal. All right? Guys, you are taught by Polly. We are social animal. So similarly, right, Team 1 will be row 1, and you see your quiz grades. So you see all of you receive ones now, because this is just for Polly to communicate that you guys have completed these quizzes. Okay, so the bonus will be added later on when the teams are more stable, and Polly will check back to the quiz 1, quiz 2, quiz 3, as well as quiz 4 and 5 more carefully, and make sure that I award the bonus credits. Now, participation is the part that's the most complicated, especially for the first 2 weeks. We don't even know who's staying, who's going. Because NTU, I don't know, I think in most of the universities in the States these days as well, the popular courses are going to be popular. And and you are always waiting to see if there are vacancy opening. And that might still happen in the second week. So until we are more sure who's staying and who's not, then we'll generate this table of all the actual participants, and then we'll start giving the participation marks. And no worries, all the YouTube chat participation are recorded as well. So Polly will take a photo of all the communications. So all those are digitally stored, so no worries. And you will see for each week, you'll be graded in 5 categories. Okay, so first category, if you look at column D, that's the YouTube chat. And second column, the score chat. F column, the office hour, in case you come. And sometimes Polly will be more generous offering the office hour points. And then the email, as well as the TA. So this semester we do have TA, and Henderson is very easy to communicate with. And I would also ask him to take a record of all your communications. All right. One thing I would like you to know is that for each category, we'll actually cap it to 5 points maximum. This is just so that you don't sort of intentionally over-interact. That's not necessary. So this is just so that your interaction will be more genuine based on need, and not overly skewed towards getting a better participation grade. Okay, you don't need to do that, in fact. All right, so for each week you will see that. And then the semester worksheet, you will see that the PA part accounts for 35% of the semester grade. So definitely, okay, work hard for the PAs and make sure you complete it ahead of time so that you can check whether the solutions are what's expected. Okay, if you go through the PDF files, you will see that for all of these PA solutions, particularly from PA2 to PA9, Poly offers a binary executable. That is, if you execute that on the workstation and run some tests, you will see that what we expect as answers. So you can run your solution and compare that against the answer from the sample binary, okay, to double check. All right. So second is D column. That will be the quiz. That's 30%. Hey, it's substantial. Participation itself, 5%. I would say, when you are at the level between A+ and A, participation will be crucial. And 30% will be exam. And for the exam, sometimes you will see that it's more that you try working the best you can. Getting too nervous about it can compromise your performance. I guess you guys all have some experience about taking exams. It's a little bit hard to say that, hey guys, take it easy, because that usually doesn't work. Again, take my advice. When you feel nervous, anxious, trigger analysis part of your brain. Trigger the part that you analyze, you exercise analysis, okay? Think why you are nervous and why anxious. Okay, and do that a little bit earlier before the time of exam, okay? That might help. That might help. A lot of times it's already too late. And it doesn't make sense anymore. And I have to say, grades are important, but it's not everything. And just keep in mind, each of you will still be respected for who you are. The grades are not the reasons that you are respected. Okay? All right. So Polly is trying the best she can to teach a class so that you guys spend the minimum amount of time, but you learn as much as the other classes do. Okay? So let's see if this continues to work. And therefore, we need to come back to the actual content. So this is topic number 1, physical media. Recall yesterday, right? We started talking about the cables for the access networks. And we went through generations of Ethernet cable. Yeah, Cat 5, 6, 6A. Nowadays we have Cat 6, and some of the cable claims they are Cat 8, but I really doubt. Today, we'll continue to talk about the other cables, particularly what about the cables for the cable modem system, right? What about the cables for the fiber to the home? And what about these wireless cables? These are also called the unguided media, recall? So this next video, we'll see the rest of all these other cables allowing access to the internet. And this is 4 minutes and 30 seconds long. Next in line is coaxial cable. And this picture shows pretty much the structure of such a coaxial cable. What it meant by coaxial is that they have 2 layers, concentric, and these 2 layers of coppers allow you to send signals. And because having 2 layers, it kind of allow the modulator demodulators to easily cancel out the noises. And so data goes bidirectional on such a cable. A very primitive form of this coaxial cable was used by the legacy Ethernet. Yeah, by baseband, it meant that the bandwidth is really, really small, very low rate transmission, and it doesn't exist anymore. But then cable network picks it up, but enhance it somehow so that they can send multiple video programs over it, allowing multiple channels on the cable. And the cable exactly used by the cable network is HFC, the hybrid fiber copper cable. Oops. And the third is the fiber cable. Okay, so this is entirely glass-based fiber, and the bits are being sent as pulses. Okay, like that. It works in a very high speed. You can go up to hundreds of gigabits per second. These high-speed fibers are oftentimes used by also the internet backbone, where lots of data are being exchanged. It's also used by the data centers, where there are always high volume data that needs to be stored or retrieved. These fibers, as we heard, FTTH, some of them slightly lower end is used for residential access as well. And they are very high speed, partly because it's very low error rate, because they are more resilient to white noises, background EM noises. The last media is the radio link. This one is very special. It is in fact the one that's used by all wireless and network access technologies. So what's listed here are just a few examples. Terrestrial microwave operating at about 45 megabits per second maximum. Wi-Fi, well, depending on the version, could be lower, 10 megabits per second, or half of 100 megabits per second. Wider area wireless access, 4G, for example, goes up to a few megabits per second. 5G is now tens of megabits per second, okay, with the potential going higher than 100 megabits per second. And satellite radio. Yeah, the bandwidth range spans wider with satellite, probably because of where the satellite is exactly and the technologies being implemented on that satellite. It can go from kilobits per second to 45 megabits per second. But one common feature is this. For satellite links, end-to-end delay will always be much longer than all these other wireless link access. Now, as to exactly how long the end-to-end delay is, it really depends on where the satellite is. For geosynchronous satellites, which sit higher above above Earth, the delay will get longer. The low altitude ones being lower, then shorter end-to-end delay. So, radio links, very special. Essentially, we are sending bits through these electromagnetic waves. There are no physical wires, so it's called unguided media. Data can go bidirectional. Well, in fact, all directional. Which is a good and a bad thing. If you think about the propagation of these electromagnetic waves, it can be influenced by environmental effects. Having objects around, the objects can obstruct further propagation of the electromagnetic waves. And some objects might reflect, these waves as well. And the waves can be interfering with each other, coming from different sources, or even coming from the same radio source. It's called the multipass effect. So physical media, radio, it's very convenient, but you see the challenge of transmitting signals through these magnetic waves. You see also generally the wireless links, the maximum capacity usually lower than the guided media's capacity.
All right, so that was chapter 1.2. And now we move on to chapter 1.3, where we talk about the core of the internet. Okay, so the first video is Polly going through the core of the internet, particularly looking at the hardware components and point out some of the interesting features of all these devices in the core. And then introducing two general design philosophies designing the core of a network in general, not particularly internet, but designing a communication network in general. And you're probably seeing it, you are seeing it on the side, circuit switching and packet switching. So this video, 3 minutes, a high-level overview of the core and the two design philosophies.
As access network is concluded, let's move on to the next component, the network core, which is a mesh of interconnected routers, as I'm trying to highlight here in red color. So you see a bunch of routers very well connected to each other. By well connected, let's see, if you count how many connections this router has to the rest of the internet. 1 here, 2, 3, and 4. 4 connections. Look at this one. How many connections? 1, 2, 3. Look at this one. It's an edge router, all right, but how many connections it has to the rest of the internet? 1, 2, and here, 3, 4. But if you look at a end system, such as this one here, how many connections it has to the internet? Just one here, through the Wi-Fi AP. Look at this PC here, only one. One very clear distinction between these routers to all these end systems is exactly in the connectivity, the number of connections they have to the rest of the internet. For routers, very oftentimes you see more than 2, including 2 connections. For end systems, just 1. And the reason that the routers oftentimes have more connections is because their role are just to transfer data. So it takes us to this very fundamental question. How do we transfer data in such a well-connected mesh network? In general communication network design, very general communication network design, there are 2 major mechanisms. First, circuit switching. Second, packet switching. Idea is quite straightforward. In circuit switching, from the source to the destination, let's build a dedicated circuit, and this circuit is going to be reserved through the entire time of communication, so we could just dump data in, and the performance is guaranteed. And this is the mechanism used by the traditional telephone network. The other technique, packet switching. Instead of allocating resource, creating a dedicated circuit, let's just use the entire link capacity. And let's send data out no matter what. But we cut the data such that it's sent one chunk at a time. And to call such a chunk of data, we have this term called packet. All right, so it's almost like a package, but packet means also a little package. Okay, so we send data in smaller chunks, but use the entire link capacity. Okay. And to tell you ahead of time, internet or the data network is taking this packet switching approach. All right, so you get a rough idea. Next, let's talk more about the circuit switching approach. So in this video, you will see Polly introducing the notion, okay, that the circuit switching people, okay, impose on the circuit switch network. But what I can say in one word is that so this approach is very reservation based. Okay, so resource is dedicated for a particular user. Oh, and by the way, the video is a little bit long, 6 minutes and almost 20 seconds. So this is the longest so far, but you want to pay attention so that you get a better idea of what circuit switching is doing. And by the way, this is the mechanism used by the traditional telephone network. All right, now let me elaborate circuit switching a little bit more. This is the familiar network. But this time we see on the network there are two circuits. The red circuit connects this end to this other end. Similarly for the blue end. And to establish such a red circuit, which is also called a call sometimes, and the time it takes to set up such a call or such a circuit is also called the call setup time. Okay. And the reason that I need to mention that term is because that takes time, because resource reservation is required going from one end to another, which means this is the first link on the circuit. We need to reserve a certain amount of bandwidth to guarantee that data gets transmitted without any loss or delay. So you reserve link bandwidth for the call. Data is going to go through a switch. This is the first switch. On the switch, memory, CPU, buffer space will also need to be allocated and reserved. So that is what I meant by switch capacity here, to guarantee that the packet will not experience delay and not experiencing any loss. Similarly for the second hop, for the third hop, fourth hop, fifth, sixth, seventh, and eighth. When all 8 hop, link bandwidth switch capacity reservations are done, then you build a circuit. But then you see, as Polly was describing, this circuit here, resources are all dedicated. When data are being passed to, no delay, no loss. Really nice. And we call that circuit-like performance. That implies delay and no loss are guaranteed. Low delay, no loss, guaranteed. Similarly, for the blue circuit. And this is really nice because zoom into this segment. This segment here shared by the blue circuit and the red circuit. The two of them, although packet or data will be going through, but these data will not interfere with each other, not incurring delays to each other, and not collide to each other. No packet drops. These days, where we do online meetings a lot, having live YouTube channels a lot, we really like to have this circuit-like performance. This way, we don't have to worry that the internet is going to go bad and the live stream is going to break at some point. Nice. Because for certain applications, we do need this type of quality of service. But, you see, establishing the red circuit, we need 8 hops, and each hop takes some time to reserve resource. So there's quite a bit of call setup time involved. This is the downside of circuit switching. Another downside is this. The way we are allocating or reserving resources over the entire path from the two ends of data communication is more. We divide the link bandwidth into smaller pieces. We divide the switch capacity also into smaller pieces. And once we do that, we allocate individual pieces or combinations of pieces to an individual circuit or individual call. But once you do that, if there are no data being sent between the two ends, that piece of resource will then be idle. If you think about it, in a way, it's a waste of resource. If the two of them ask for resource and a call established, but they're sitting doing nothing. So not very good utilization of resource. So this is the second disadvantage of doing circuit switching. Now, speaking on dividing link capacity into pieces, there are multiple ways of doing that. First one is called frequency division, the other time division. This is the second time we see the term FDM. Where did we see this? Yeah, cable modem. We divide cable modem capacity. We divide the cable network link capacity into what? Pieces by the frequency band. This is a very different flavor. Okay, it's dividing the link by the time. Let me illustrate. The example on the top is doing FDM, where we divide the entire frequency band there to 4 users in equal division. So full frequency band, 1/4 to the blue user, 1/4 to the green user, to the yellow user, and the pink user. TDM works this way. Instead of dividing the frequency dimension, that's divide, okay, in the time dimension. So with these time slots, we allocate the time slots in a rotating fashion to the 4 users like this. Blue, green, yellow, pink, blue, green, yellow, pink. Yeah, it's rhythmic. That is exactly how TDM works. With a good rhythm, with well-synchronized time, the 4 users can send data one after another. Very orderly. If we have more than 4 users, how do we do that? You see, we could further refine the division into, for example, A parts. That way we can accommodate how many users? A users. Similarly for TDM.
All right, now you get a rough idea, right? So circuit switching works in a way that, hey, let's build a circuit from the source to the destination ahead of time. And then we pass data. And this data would just flow smoothly throughout. But then you see that there's a call setup time initially to build that circuit. Now, let's exercise through an example so you know a little bit better how you transfer a file and estimate the time it takes to transfer a file. So here's the video, short, 1 minute, just to set up the example.
To make sure you pick up circuit switching and how it works, let's see if we can work out this problem together. The question asked is, how long does it take to send a file, this big, from A to B over a circuit switch network? And in this network, all the links have the same capacity, 1.536 megabits per second. And each link is divided to 24 parts using TDM. And meaning that circuit between A and B only gets 1 slot. And the presumption is that to establish the end-to-end circuit between A and B, it takes this much time. All right, so how long does it take entirely to send the whole file through? Let's work on it.
Okay, so let's work on this. And interesting. So I guess my screen capture crashed again. So allow me a little bit time here. Very interesting. Uh-oh, it's not working this time. Ouch. Oh, okay, no worries. There we go. All right. Okay, so this was the example. Okay, we want to send a file of this many bits. So this is k bits. And so we are transferring the data from A to B, and all the links, okay, are the same size.
So no matter how many links there are between A and B, this is the bandwidth. But we need to divide it into 24 parts for each of the users. So for this file, I think we get only 1/24 of the entire bandwidth for the link. And how much is this? Okay, that's hey guys, help me out here. Calculator. 1.536 divided by 24. There we go. So what I have here is 0.064 megabits per second, and this is 64 kbps, right? And so we have this much to send and this much capacity. So I think we will need 10 minutes, 10 seconds to just pass the file. But you see that there's also a call setup time. So this is to establish the end-to-end circuit. So the eventual amount of time required, so we need to add 0.5 second as well. So that will be 10.5 seconds. Okay, I hope that you guys, thank you, Ting Chi. Yeah, it is 0.064 indeed. Okay, but now you get an idea. So you calculate the amount of time to transfer the file, but you see that for the entire transfer to come out of point A to point B, you need to also include the call setup time. Okay, so it would appear that once there's a circuit, everything will go smoothly, but one needs to spend time to figure out what that circuit is, okay? And that could be time consuming as well. So that was circuit switching. Let's move on to the second flavor, packet switching, okay? So once again, the Polly introduced the packet switching notion. The idea here is more that you get served as you arrive. You get served as you arrive, and everybody might come in and then join and waiting a line. So there's a special term, congestion here, happening in a packet switch network. So this video here, 3 minutes and 40 seconds, introduce you guys the packet switching notion. Now let's discuss more about packet switching. The mechanism is very simple, right? We simply cut the data into small packets. And as the link is available, pass it out. So each of these small packets will go on the link in full bandwidth. So if you consider L being the size of the packet length, and R being the link bandwidth or the link rate, the delay, this being small, this being large, to send a packet very small. This is one advantage. And then think about this, if you get two users, A and B, both are generating data and both are sending these packets out. If A is idle, not sending, and B comes up with data, B can send out, no problem, and in full link bandwidth. Similarly, if B is idle and A has data, no problem sending out. So there's no such a situation in circuit switching where B allocates all the resource, gets all the resource, and A having data to send, but A didn't get any resource as a result. B sitting idle, occupying all the resource, and yet A having lots of data wanting to send, not getting anything. Okay, so there's no idle waste there. Last is maybe a little bit less obvious. You see, bandwidth is used as full, so there's no need of dividing the link bandwidth into pieces. So the mechanism is also simple. Okay, being simple, there's no idle waste, and there's no call setup, resource reservation process required. Okay, packet switching can potentially be very efficient, especially for short data streams. Think about the resource reservation delay, the call setup time. It can be pretty long, and if you have very short data stream, then hey, the overhead relative to the entire need of sending data is high. So you can probably imagine now, data network, internet. At the beginning, we were just sending really short emails. It doesn't make a whole lot of sense just to send an email and you go all the way to set up a circuit. So another advantage of using packet switching is also because of the user demand. Now let's look at what's wrong with packet switching. First of all, we will have resource contention because there's no reservation mechanism. What if A and B, they all have a lot of data to send, so the resource demand is beyond the available resource. So we call that situation network congestion. In that particular situation, packets will have to queue up at these routers and wait for link queues. So you see here, wait, the keyword. Delay here to transmit a packet is short, but there could potentially be wait that is a little bit uncertainly long. Okay. And hey, packets will get queued. What if there's not enough space in the queue? Packets also get dropped. So in packet switch network, we do have substantial delay. We could have substantial packet losses. One big disadvantage. Another disadvantage is here. This one is a little bit subtle. In packet switching network, there's no circuit being established. The way we send packet is that you forward it out on the link. The next router will need to pick up everything. So you need to wait until the entire packet is received. The next router will need to receive the complete packet before the router can further forward the packet. So this is called store and forward. So the router action there passing packets is store the packet first and then forward the packet next. So this mechanism here is determining how packets are moved, okay, one hop at a time. Meaning you have one of these L divided by R every hop, every router.
All right, now you hear about packet switching, right? So there's no idle wait time. Nice. But there's congestion and the time it takes to do store and forward. So similar to circuit switching, right? Circuit switching also has something nice. Hey, once we build a circuit, data is going to go out smoothly. There's no such thing as congestion. There's no store forward. But on the other hand, there's an initial time, right? Initialization time, the call setup time. So you see, both have their advantages and disadvantages. Now I ask you here, if you move to the, oh wait, very interesting. So the chat is not showing now. Okay, give me a second. There. Okay, I'm now seeing, you guys are now seeing the chat. Sorry for the glitches. Yeah, so there's a pop-up question now. Polly asks, between circuit switching and packet switching, which way of data transferring you like better intuitively? Okay, guys. Oh, okay. Yasin actually posted something. Depends on the context for live streaming. Oh, okay. So Yasin actually says that for live streaming, he thinks that and packet switching might be better because it doesn't mind losing packets. Email better using circuit switching. Okay, interesting. So I guess Yasin, your intuition is that with packet switching, right? There's congestion. Packet might get dropped, as Polly mentioned in the video, and that's not going to be reliable, right? For emails, it's not a good thing, okay, to have packets missing or a part of the email missing. Okay, I see the intuition. Chen Jie here says, okay, he likes packet switching better because it uses the best of the resource. Okay, interesting. Let's see, Yixin. Okay, Yixin likes circuit switching better because it endures, less delay and loss of transmission. Because circuit switching, once you have the circuit, there's less delay, at least less delay variation. And there's no lost data. Let's see.
停棋 circuit switching because yeah, okay, and it's very intuitive for 停棋, suggesting circuit switching. Because it's invented first. Okay, that's an interesting reason. It feels more adaptable. Packet switching, I think Manlam likes packet switching better. More adaptable. Interesting. 又成 packet switching. You don't want the initial way because the initial way can take a long time. And you might get rejected. In fact, it's called the call reject. Okay, in case there are so many people occupying the links between the source and destination, and there's just no possible, there's not enough resource to establish a call, you might get rejected. 有成, you are right. Yeah, I think the opinions is somewhat split, right? Some like circuit switching better, some like packet switching better. I thought we were as more intuitive. No, it's okay, 婷琪. Yeah, it's okay. Crazy ideas or suggestions based on psychological intuition can sometimes be good. So as long as you are offering something different. I guess what I want to communicate in this course is this. Being right, of course, is cool, right? And I actually find a lot of times being different is cooler. Particularly in the 21st century. All right, so I don't know if you agree. Okay, once again, you guys can be different. Whether you agree or not, it's not important. I actually appreciate that you are different. Okay, yeah, guys, look at each other's answers. Circuit switching, packet switching. Yeah, packet switching. 正年 prefers packet switching. There's no setup time. Circuit switching, more stable once the connection is established. Yeah, I guess those who play games, guys, if you play games, I guess you guys can associate with playing games, right? If you are connected, you would really like the game session will be smooth, isn't it? Otherwise, there could be things that are unexpected and you're working in a team. That's particularly the case that you don't want interruption in the middle or jitters in the middle, because then you will have a hard time coordinating with the teammates. Packet switching because the entire internet runs on it. Okay, sure. If the internet is popular, right, already, and internet is designed based on packet switching, there must be something nice about packet switching. Okay, I like this way of thinking. Okay, think more why internet is popular. Maybe it's not because just being a packet switch network. Guys, some of you guys' intuition are very good because packet switching is also flexible. One can actually simulate a circuit switching behavior, in fact. All right? Sorry that I shouldn't say that, because if I said that, your intuition changes. So guys, you see, your intuition is based entirely on what you know, in fact. So that intuition does not come out of blue. It's actually a result of implicitly learning things. Got it? Great. I like to see you guys thinking and debating. Feeling a little bit less confident, but more confident and less confident and more confident in this cycle. Okay. You know what, guys? Let's talk about this store and forward thing, because this notion is oftentimes, I don't see you guys mentioning, hey, you don't like packet switching because there's this store and forward thing. The store and forward thing is a little subtle. So next video explains if you have the store and forward feature in a packet switch network, the way you calculate delay also is based on this phenomenon. You need to store packet and forward packet. So let's check out a numerical example. We calculate the delay to transfer a file. Okay, how about that? So this video, 3 minutes, almost 4 minutes. So here let me illustrate the store and forward effect to the end-to-end delay. So consider this scenario. The source is over here. Okay, user typing up things and generating these small packets, 1, 2, 3. One router here in the middle and receiver on the other side. And each packet here the user is generating is L bits long, and the link bandwidth is R BPS. So you see, to send this big packet over the link at this speed, this is the amount of time that's required. And on a packet switch network, we need to store the packet entirely before forwarding. So entire packet needs to arrive at the router before it can be transmitted further. The end-to-end delay will be what? 1L divided by R for this hopping, because this guy, to send it out, it requires L divided by R. This router here receiving it waits until all is received, and then what? Send it out again. That's another L divided by R. So if L is 7.5 megabits per second, R is 1.5. You see, each hop, 5 seconds. 2 hops, in this case, how long? 10 seconds. 3 hops, the longer, the more hops you have, the delay of sending the packets longer. This is different from circuit switch network. Bits can be streamlined. Okay, there's no need to store a bunch of bits first before forwarding it. Okay, that is saying that each bit arriving here gets out quickly, so there's no hopping. It's just the propagation delay and the transmission delay, L divided by R, from the first hop. This slide is to illustrate congestion. The scenario is A and B, 2 users generating packets, A generating blue packets. A generating green packets and B here generating blue packets. And you see these packets are generated as user A and user B are typing things up spontaneously. So green and blue, they will kind of bunch up or multiplex in a random order. Okay. Unlike in TDM, time division multiplexing, everything goes rotating, rhythmic. And this, okay, having some sort of spontaneous behavior in it is statistical multiplexing. Okay, so on packet switch network or on the data network internet, packet kind of, multiplex to each other randomly, spontaneously, depending on how they are generated. Now let me draw your attention here, the router. You see packets in case the outgoing link then was small. An incoming link here, this is 100 megabits per second Ethernet. This is only 1.5 going out. Chance is very high. A and B, if both of them actively generating lots of packets, the packets will have to wait here in the queue before they get the link used. And if there's not enough space here for the queue, the next one, the green one coming here, will need to be dropped. But there's no memory space to hold. And those packets waiting in the queue, it depends on how long the queue is as they comes in to the router. The queuing delay can vary. It can be a little uncertain. But transmission delay, the time it takes to go on this link is always the packet size divided by 1.5 megabits per second. And we use the full link bandwidth. So transmission delay here is very easy to get. All right, so that video is there so that your intuition of what packet switching is a little bit more clear. All right, guys, it's time to take a break. It's 11:14. Let's take a 10 minutes break and resume the lecture 11:24. And we'll come back to compare circuit switching and packet switching a little bit more. All right, see you in 10 minutes. All right, time to come back. Good. I don't know if you read each other's answer to the pop-up quiz. Yeah, so I can see also that you guys are trying to, again, as I said, right, learning from each other, and then so you kind of adjust your intuition one way or another. So that is also a part of the learning process. Okay? Sometimes if you jump directly to there's a correct answer told by somebody, then you sort of miss this opportunity or this part of learning. Good. Now let's compare circuit switching and packet switching more. using a numerical example. How about that? So this example is a video that's about 2 minutes long. Here, let me use an example to illustrate. Packet switching actually outperforms circuit switching when there are more users, and each of these users are not exactly very active, sending short messages only each time. All right, so scenario is very simple. Okay, we do have a network of end users, and they're behind this router. Going out of the router is a very low bandwidth link, 1 megabits per second. And each of the users is behaving this way. When they're active, they do need a lot of bandwidth, 100 kilobits per second. But they're only 10% of the time active. In a circuit switch network, in order to satisfy these 10 users, and each at maximum requires 100 kilobits per second, so we reserve 100 kilobits per second to each of the users. And how many users we are allowed to reserve bandwidth? This is 1,000 kilobits. So we can only allow 10 users, okay? 10 circuits. But in packet switching, you see, the users are only active at 10% of the time. Consider this scenario. If we have 35 users, right? The only situation that these 35 users will have trouble sending data out is when there's at least 10 users being active at the same time. So what is the probability of these 35 users and more than 10 of them being active at the same time? If you do the calculation, you'll see that it's very low. So 99.9996% of the time, in packet switch network, 35 users will do well. No trouble. So if you do have a lot more users and each of the users needs just a small portion of time to send data, which one would you pick? Circuit switching or packet switching? It's quite obvious, isn't it? And oh, by the way, anyone here knows how to derive this value? The probability of 10 of the users being active at the same time, given the active rate is 10%. Yeah, so now you see with an example, the intuition gets rebuilt again. That the internet, the reason that it's in packet switch fashion is so that we better utilize the resource. Okay, because with a very high probability, we can accommodate more users, and most of these users will not feel any glitches at all. Okay. By the way, I asked in the video if anyone know how to derive that very, very low probability of 35 users using the channel concurrently. Post it on Ask Us Anything. You get extra credit. All right. And you know what? That's time for quiz 5. Okay, and let's go to the whiteboard mode. So this is quiz 5. Circuit switching, you know by now, right? So what we do to send data is we reserve a portion of the network to pass the data. In packet switching, however, we actually cut the data into packets and then pass them in a mixed way over the network. So quite different. And what poly does is oftentimes is exercise association. So for example, if we will be transferring water instead, okay, so that's not transfer data, that's transfer water. Circuit switching will be like, hey, building these water pipelines and dump the water through the entry point, then the water will get to the destination. Packet switching will be more like preparing a bunch of these buckets and placing the water in the buckets and then having people or machines passing the buckets one hop to another, isn't it? Good. So that's exercise association. Q1 here asks, what do you think about the car network? The network that's transporting cars. Is it designed more in a circuit switching way or packet switching way? But mostly tell us why you think it's more circuit switching or it's more packet switching. And what about the train network? Yeah, we do have a railway system, right? That we pass these trains around. Is it more circuit switching or packet switching, and why? Q3. This is once again, which one you like better? Polly has already asked this as a pop-up question on live chat, but that was, a little bit earlier before we run the example. You see the benefit of statistical multiplexing. Okay, is your opinion changed? Okay, does your intuition shift? Okay, so which one you like, again, personally, better, and mostly why? Okay, guys, let's go to the score space. I hope that there are no glitches this time. And for quiz 5, there, okay, the question is in place. Guys, you have 7 minutes, and if you have a team already, gather your teammates and discuss away. So just leave a little bit time so they can type up you guys' answer. So let's start counting time. It's 11:31. Let's check back. 11:38. Okay, so hey guys, for starting from quiz 5, could you also let me know your team number? Okay, that would be really nice. So Amber and Cheng Jie, could you edit the team number? Okay, at the top of your answer. So just edit your answer real quick. There you go. Thank you, Cheng Jie. And there you go, Katie. All right, good. I see many of you are typing, so you've already converged to something you want to say. Then let's check out some of your answers. So Team 10 says, okay, they feel that car network is more packet switching like because they share the cars share the roads. Okay, good. That is indeed an important key word in packet switching, right? The In data network, the data share the network. Similarly, the cars share the vehicular networks we have. Now, there will be congestion. Okay, this is another keyword that shows up when we introduce packet switching. So it seems very much to Team 10 that the car network is packet switched. Yeah. Cars does not need to reserve a road in events. But you know what, Amber? Have you guys think about these carpool lanes on the highway? Is it a type of reservation? Guys? Yeah. Interesting, isn't it? In a packet switch network, there seems to be a certain flexibility. You can implement some degree of reservation. Interesting. Circuit switching for the train network. Let's see what are the thinking behind the answer. Of course, you cannot have multiple trains going on the track at the same time, isn't it? Yeah, there will be serious collision, and we definitely don't want train collisions because more often they are many people on the train, and the trains typically travel in a higher speed. For safety issue, definitely the train network, and also as a mass transportation system, are designed very often in a circuit switching fashion. Hey, safety, very good reason. Packet car. Well, hey, dropping a data packet is not much a loss, but hey, losing life it is, right? So it really depends also on the content, the things that you're transporting. Packet. Okay. Team 10 likes the packet switching network. More convenient and flexible. Okay, this is the first time I see that people saying being flexible as a strength. Team 12, packet switching. Okay, yeah, I see that maybe most of you are thinking car networks are packet switching, and the railway system is more circuit switching. And Team 12 also like packet switched network better. It's a better use of resource. Okay, utilization. This is one of the reasons we see already in the live chat, right? And it's becoming clear. Let's see, Caitlin, Team 2. Car networks don't have fixed path, indeed. Okay, make more logical sense to enact packet switching. Car getting to one traffic light, and getting, cool, you find a similarity in car network as well as the packet switch network, right? So at the intersection, that seems to be a point of congestion. Yeah, the cars might need to queue up, waiting for these traffic signals. Train networks, fixed routes, definitely. It's very circuit switching, isn't it? Yeah, and there's a predetermined pipes, and somehow the trains are not colliding to each other. And if you think about it, right, the joints of these rail routes, train routes, it's not exactly like a circuit when you have reserved the resources dedicated for a particular connection. In train network, you see some differences, right? That intersection, of course, you cannot have multiple trains intersecting at the same time, but they can somehow schedule at those junctions, as long as the trains won't collide to each other. So that junction is not reserved for a particular train. It's still utilized by multiple trains. It's just that the trains don't collide. So the kind of circuit switching they do there in the train network is different from the circuit switching network we just talked about, okay, for data, for telephone network. And you can see that the train network circuit switching is more efficient way of utilizing resource. Hey, again, we're talking about resource. Guys, you think that the packet switching can be more flexible, but you see, one can also design the circuit switching in a way that you are more considerate. and therefore introducing flexibility in there. So again, hey, your intuition are rebuilding itself. I prefer packet switching as it allows more users to use resource. Guys, you seem to like such that the resources can be shared by more people. We do live somehow in a era that the resources are more scarce than we think. Okay, so let me give. I just want to let you guys know that, hey, being the first or the second or the third, that doesn't necessarily earn you extra credit. But hey, if you have answered already, definitely speak truly of what you think. Okay. Yeah, seeing packet switching. Circuit switching again. Just follow rails. Yeah, because trains, oftentimes people expect we travel faster taking a train, right? Congestion is definitely not a good thing. But guys, think again. I was visiting a university last semester in the States. I took Amtrak several times. Okay, so Amtrak is the rail system in the United States. You know what? I run into congestions quite frequently taking Amtraks. I guess you can design a circuit switched railway system in a very packet switched way. So I guess, I don't know if you guys have experience taking Amtraks. That is my experience suggest. All right. Okay, so Yasin, good to know that you dare take a different stand. Normally choose circuit switching. Since I hate traffic. Yeah, we all hate traffic. But since congestion is highly improbable, given a reasonable number of users, I would prefer packet switching. Particularly for data network, it seems better, right? Because there are other ways of recovering from packet loss. You don't know quite yet how, but you will see definitely later, and you will realize also more, and you will see the reasons more why internet is packet switched. Car network, packet switching. Train network, circuit switching. Guys, yeah, it's natural that probably go a little bit faster. I would go for packet switching because, I see. So I enjoy very much. I think you guys would enjoy also seeing others' opinion. Because, hey, learning is like this. You see more, then you will converge easier, better, and more comprehensively. Okay, what do you think? Circuit switching, very good. Yixin, okay. It gives me a sense of safety. Yixin, interesting. I guess you don't like uncertainty. Polly doesn't like uncertainty either. But Polly learns to live with uncertainty and lives to adjust how I can handle the anxiety coming out of uncertainty. I prefer packet switching. Okay, so this is 正年. For scenario like internet, there are lots of users. Yes, we do, right? We are all accessing internet. Okay, using circuit switching is very, very hard to allow so many people accessing internet. Now you see, right? Why does ring rule all the previous pre-existing network, the data network, the internet? Maybe a car accident like a packet loss? Yeah. So the train network is definitely more circuit switched because accident or wait time are something that's just not good for train travel, despite the eventual experiences. Packet switch network. So 预征, circuit switching. It depends. Oh, cool. Okay. Hey, 预征, you learn, right? Allow yourself to be flexible. You answer this way. It depends. In a dense area, maybe packet switching. But for a resourceful world, okay, a place where there's not many cars, right? Why not circuit switching? So, Yuzhen, you are also saying that you observe that in certain situation, one way is better than another. In a resourceful environment, hey, it's resourceful, right? So just, dedicate the resource. In a resource scarce environment, well, hey, you don't want to reject people all the time, then the packet switch network. Okay, let's see. Team 5, 听齐. Both. Okay, good. Hey, gradually, right? You see that the team's having more time to observe from others, to think more. Hey, they started saying this way. Hey, we need both. I like both, right? One is good for one situation, the other for another. All right, Team 18, Bo Yuan says, I like the train network. Hey, you like the train network, but that's one thing, right? Because I hate congestion, and the trains give more guarantee of the worst case communication time. Yeah. Bo Yuan, you have a point. In a packet switch network, so in a train network, every now and then you still get delayed. You might miss a conjunction because the operator, okay, the train conductor, okay, having trouble starting leaving a particular station on time. Okay, and if more of these conductors do that, then you get a mess in a circuit switch network. Indeed. Okay, but the likelihood of running into congestion and getting delayed is lower. Okay, so, Bo Yuan, you probably care very much about time. Okay. You know what? Polly does care about time. I thought time is the scarcest resource in the world. And it's universal. Every one of us. We only have so much time to see the world, to be with the people we love. Isn't it? Money, it's scarce, especially at your age. But it's something that you can potentially expand and get more if you use your time well. So what do you think? Okay, that's not a question. Don't answer me that question. So that was Team 18. Very interesting. Bo Yu, let's see. Packet switching, better for most cases and flexible. So the better here probably mean many things, right? It's good also for a real-time system and more dynamic system. Dorothy, Team 3. Guarantee, no condition. All right. Yeah, I can understand, right? For example, when you're traveling by air, wouldn't you like to, take the business class or the first class where you don't need to wait and guarantee the fast service? So you have this certain sort of ease, okay, having a guaranteed service. Ray here says, I prefer packet switching. It doesn't waste idle time and don't need to set up. Definitely, right? And we sometimes learn, right, what's rush hour and what's not rush hour. And those who observe well can get away from conditions, okay, or plan ahead to avoid conditions. Interesting. So the packets can perhaps be smart, or the senders of the packets can perhaps be smart. All right, Team 17, let's see. Packet switching more. Great to see that. Utilize the whole bandwidth. Yeah. So, guys, those who like packet switching more because it's a better utilization of the resource, consider being a politician. Okay, we need more people like you. All right. Highway. It depends. Is better for the internet because it's efficient and share resources like we said. Guys, don't you find that it depends is a perfect answer for any question? But you need to say in what case one is better, the other case it's not. Let's see. Ethan. I would prefer packet switching because there is a better allocation of resources, even though this may cost a longer time to transmit. Yeah, because of congestion, because of store and forward. Continuing the analogy for the train and car network, train networks are more expensive to build and maintain, which may mean circuit switching may cost more in the long run. This is a very unique viewpoint. The train system is indeed costly. So thinking of cost effectiveness here, I mean, cost effectiveness is an important factor we all know. It's just that not always we think of that. Ethan, thank you bringing this perspective, right, to the class. Indeed, I guess for many regions, building a train system or the mass transportation system, cost is always a consideration. Okay, if you want to sustain that system from continuous, you want to sustain the system for continuous long-term operation. I guess that's why you build such type of system only in a dense populated area, right? Makes sense. Yo Cheng says, I like packet switching because it has a better resource utilization, definitely. But in the transportation, train better, environmental friendly. Hey, guys, yet another perspective, right? For train network, circuit switching is more environmental friendly. It is, isn't it? It's more costly, but recovering from environmental damage can cost even more. So thinking in terms of cost effectiveness for a pleasant living space, yeah, very good argument. Love to see more different perspectives or unique perspective. Loy here says, packet switching. It's efficient and it doesn't waste bandwidth. Okay, it's just hard to. Okay, Loy just couldn't bear seeing resource put to waste. Okay, very good for you. And Sherwin says, packet switching. It's more scalable for larger users base, definitely. Xingwen says packet switching, it's much more flexible and expandable, definitely. Okay, yeah, we've seen this earlier, right, in the arguments. Yeah, people started saying that flexibility is a strength. It is a strength, isn't it, if you think about it, right? If you want to change it later, or if the initial design is not that good, right? It's easier to make changes. That's a strength. It is a strength. Hey, wait. Okay, good. Team 10 has follow-up answer. Yes, sometimes car traffic system will behave like circuit switching. Okay, so this is to address my comment saying that we have these couple lengths, isn't it? In traffic control, a section. And that carpool can sometimes be activated only at a particular time duration in a day. A time period in a day, yeah. Oh, and hey, there's something, right? Ambulance, right? When the ambulance is coming from behind or either way, as long as we hear the siren, what do? We yield. Guys, Don't think we yield simply. So, hey, what is this? What is this? Can we send packets with the highest priority? Yes, we can. Can you do that in a circuit switch network? Can you break other circuits and send a special circuit? You know what? In the circuit switch network, we do have that design. The telephone network, right? The 911 call is actually going a different circuit. And that one has the highest priority. So you see that in a circuit switch network, one can also set priority for the circuits. And you see that the circuit switching and the packet switching are just big major notions. And if you develop more, you can come up with something that is perfect for a particular scenario, for a particular application. Amber, great. Guys, you guys had high potential there, showing different perspectives. Vincent, Team 22, I prefer packet switching because it saves a lot of idle time. Yeah. Okay, this is good utilization of resource. Yeah. I guess as the world population continue to grow, this is an issue. 预期, it depends. I like car network, want flexibility, but I like the train network as well. If I'm in a hurry, It sounds perfect. Sounds perfect, 预期. 建伟, let's see. Packet switching is better. All right. Yeah. Even if it's somehow congested, it can be somehow congested, but it still allow more cars to travel. It is, yeah. And maybe there are things we can do such that we can navigate the cars around the conditions. Okay, so hey, we have Google Maps, don't we? All right, good. Guys, we are spending more time obviously going through all of your answers. And this is what Polly will do more in the quizzes, especially the open-ended quizzes coming up. Okay. This is very good exercise for you guys to see how I grade students. Okay. And how I think the real world judge you. Good. Let's come back. We can now finally summarize how circuit switching, packet switchings are different, but eventually internet is implemented in a packet switch fashion. All right. After the discussion trying to solve the quiz, what do you think? Packet switching versus circuit switching. Do you think packet switching is the slam dunk winner? Is data network internet's way always gonna win? Probably not always, isn't it? It's great for short bursty data, right? Short amount of time, but sending lots of data. Because it promotes maximum resource sharing, and it's quite simple. No code setup either. But on the other hand, we do have congestion. Packet delay might be unexpected long, and probably worse, there could be packet losses. And so you need additional protocols, yeah, because of the way the very low level packet forwardings are designed. So we probably need extra mechanism at the higher layer to ensure data can be transferred in a reliable way if it's necessary. And what if we want to do some level of a guarantee, for example, to do video streaming? Can we achieve circuit-like behavior with packet switching philosophy at a very low level? Can we do bandwidth guarantee? Well, people have been thinking about it, and this is still a problem that's not quite yet solved. And this is covered in Chapter 9, the Multimedia Networking chapter, later on in the textbook. And we unfortunately won't have time to cover this semester. All right, good. So now you see that the internet is designing a packet switch way, but don't judge internet too quickly. Okay, thinking that congestion is gonna be, everywhere, and people are gonna hate internet. Don't judge too quickly to anyone as well. Now, let's talk a little bit more about packet switching. Because we say that we break data into packets and we pass one packet at a time over a packet switch network. Some of you might be a little bit more insightful, thinking, hey, what if we send the file as a packet? Then it'll be like circuit switching, isn't it? Almost circuit switching. Yeah, actually, you might not want to send a file as a packet, okay, over the internet, because there are hubs, okay, of routers on the internet from the beginning to the end, and there's this store and forward thing there, okay, that you need to do. So there's time it takes for a packet to be stored on a router, some processing being done before that packet gets forwarded to the next one. So you don't want the packets to be large. So this video, about 4 minutes, explain you want the packet small. The next few slides, they are still somewhat important, okay, but not strictly talking about packet switching, circuit switching, and the comparison. So these slides are to answer a couple important questions. We said that packet switching, what it does is to divide data stream into small packets. But why not large packages? Right? We didn't really justify that. We kind of like that L divided by R. The time it takes to send one packet is small because this is small. And in case the link is really fast, then this is small. But if this is a little bit larger, well, not so bad either, isn't it? Well, think again. And this is the example that I try to use to set up the stage. And it's just a slightly extended version of the previous example where we have two hops only, just one router between the source and destination. The packet size 7.5 megabits and the link rate 1.5 megabits per second. And you see that L divided by R is 5 seconds. And because there are 3 hops, so this time store 5 seconds for, store 5 seconds for, and 5 more seconds to store. Altogether, 15 seconds to send this packet L. Now, 7.5 megabits, large, right? Sending a large package like this over this 3-hop network, 15 seconds. Let's try dividing this large message into smaller packets and see how it will work. 7.5 megabits, let's divide them into 5,000 packets. This way, each packet is only this big, 1.5K. Link rate is still what? 1.5 megabits. So to send a small packet like this, it takes only 1 millisecond. Now, look at this. This is the same network, 3 hops. Each packet is now very small. And to send one packet, the first router will take 1 millisecond to receive it and then send it out. So 1 millisecond, 2 millisecond, and only 3 milliseconds until the destination receives the first packet. And you know what? These links can work in parallel, right? Because router 1 here can be passing packet 1 while the source start passing packet 2. You're trying to do also streamlining here, except that the unit of streamlining is a small packet. You see, why packet switching suggests small packets? Because it's trying to maintain the benefit of doing circuit switching. Unfortunately, we could not be streamlining bits, okay? But let's keep the packet small. Then we get to keep some of these nice properties in a circuit switch network. And having these links that can work independently is nice. We can pipeline or streamline the sending of the packets over the network. So each link works in parallel. And the overall delay in the end is what? 5,002 milliseconds, only 5.002 seconds. If you recall earlier, if we send 5,000 small packets altogether, 7.5 megabits, each hop 5 seconds, and 3 hops 15 seconds. How much time are we saving? Big time, isn't it? This is why in packet switching, people always talk about cutting data into small packets. Yeah, but allow Polly to add, you don't want the packets to be too small either, because the data part of the packet, if the packet is too small, there's always a part of the packet that is carrying information for control purposes. For example, who's the destination, who's the source, and things like that. Those are not the real data we want to send. Those are just so for the network to know where to pass the data. So if we make the packet too small, the proportion of the data is smaller than the control bits, then there's a lot of overhead. So you're sending a lot of bits around, but much of those are just for control purposes, not the real data. Okay, so deciding what the right packet size is really depends on the network and the scenario. Next is the next video is to show you that what the store and forward is doing. You see that one needs to store the packet so that there's some processing in the router. So that processing essentially for the router to find out. If you recall, right, in the overview picture of the in the overview video of the internet core, you see a bunch of routers. And these routers, very interestingly, they often have multiple connections to other routers. Okay, the end systems, what we have are more often just a wireless connection to the internet, and that's all. So in the core, the routers are very well interconnected because then the likelihood of finding a route to go around the congestion is higher. Okay, and if you have a lot of traffic, this is just a better way of managing resources. But you see, in order for a router to find out, right, for this particular packet, which router next to forward it to, hey, that takes time. Okay, and that takes also some time for that takes time. That calculation takes time. That it takes also time to take in a whole packet. So packets arrive bit by bit. It will take some time for the packets to fully arrive at the memory space before the forwarding decision can be made. And once the forwarding decision is made, then packet gets transmitted out bit by bit. So each packet arriving at the router will take some time. And that amount of time is definitely longer than what the data will experience in a circuit switch network. So this video to explain that forwarding process. And why do we need to store packets first before forwarding it, right? This is one of the reasons that we still need to form packets. Why we cannot just streamline the bits. The reason has something to do with how the routers is working. So inside the router, there are two key functionalities, and there are two of these. First is routing. So there's some sort of algorithms there. The routers, given the graph of the network, computes the shortest route. At the end of it, we generate a routing table like this, a forwarding table like this. And the way we look up this table is by matching the destination address, okay, of the packet. And so if a packet comes into a router, inside the router takes the destination address in the packet and look up this table. If there's a matching entry, the router discover what is the next router to forward to, what is the right direction to pass this packet further. Okay, you see, router what? Oftentimes well connected to other routers on the internet. So this router here could have multiple ways of passing the packets further. Unlike the very simple scenario there, each router has only one outgoing link, right? So it's no longer that intuitive why packets need to be stored and then forward. Now you see, packets need to be stored here, and then the router can look up this field and match this entry and then discover, okay, this packet is supposed to go out on network interface 2, this direction, to this router next. Similarly, this router needs to store the packet entirely, and then it can look at the header, this particular field, destination address, and find out in its own routing table which router next to forward the packet. Yeah, it's exactly because of the forwarding functionality that's required to pass data around over a packet switch network like internet. So on packet switch network, we store packet before we forward it. So forwarding here is to move packets to routers all the way from the source, eventually reaching the destination. All right. We'll definitely tell you more as we come to chapter 5. Okay. So in datagram network or in data network, the way it works is let's receive a packet entirely, okay, and look up the destination address to determine which is the next hop. And so you see, if the routing table changed, if the graph changed, routing table would change. When the routing table changed, when the forwarding table changed, yeah, the subsequent packets might be following a slightly different path to the destination. Okay? So the routes, packet traverse might change in a session, in a data stream session. So the analogy here is that the packet switch network is a little bit more like the regular car network. Okay, if we are driving a car, a lot of times, hey, to find out the next segment, okay, which road segments we should go on, we might actually stop and pause and ask someone for this destination, for direction, or park to the side and then look up Google Map to find out which is the next segment. Right.
All right, so those are the two things Polly would like to add. You see that on the side that we have not yet talked about this virtual circuit thing. That's how internet emulates a circuit-like behavior. Okay, and you know what, guys? It's already 12:11. We don't have time to go over that today, but we'll definitely continue from that next Tuesday. Okay, with that said, thank you for your participation, and that's all for this week. And I say goodbye. Bye. All right. Bye. Oh boy. All right, guys, go on, have lunch. All right.